Thanks a lot, Nico, for the introduction. I'm really glad to be here, particularly to see how the SSL4EO community is growing. Today I will introduce basically the content is in a perspective paper we compiled together. But before I go to the topic like showing here, I will give a very short introduction about my own research. So basically the group I have at the TUM, we have two, let's say, research focus. Overall, we are working on AI data science for Earth observation with the goal to really contributing to societal relevant challenges. This then defined, we have on the one hand, application focus. Basically, we do AI for EO for social good. So we have various application focus. For example, in my previous ERC project, we tried to use AI for EO to do the mapping of global organization. We have also been working on natural hazards. What you see as example here is that we are using AI to detect volcanic deformation patterns of the South America. We also have application focus, actually not only on food security, but also on the whole green layer, meaning forests, crops, and so on, working on tasks like tree species, classification, disturbances, detection, crop type classification, yield prediction, and so on. We also have a focus on the UN's SDG. What you see here is example that we try to segment out the informal segments for the global south. We work also on crisis response, and we have a fairly big team working on climate change, where we try to tackle general machine learning challenges to support applications in the field of digital twin Earth, as you all know, the destiny, let's say, mission of the EU. Other than that, we also work on very unconventional geodata like tweets. For example, we have been streaming global tweets, now not anymore possible, but in the past, for 4 or 5 years on a global scale. And we are trying to understand globally the social dynamics. And finally, we also work on very practical things like safety and security. This is the application pillar, but our group also have probably is one of the hardcore methodologic group in this domain. We also work on, let's say, topics that are of general interest, that are fundamental for the field of AI for EO or machine learning for remote sensing. For example, we work on re-implement physics space and the domain expertise into the machine learning methods. For example, we have been developing HydroPML, which is a physics-aware machine learning platform for hydrology, basically to help different use cases like flood, drought, forecasting, and so on. We work also a lot on reasoning, meaning that going beyond a perception to figure out semantics from a satellite image. Instead, we try to figure out the spatial temporal relations from the data, understand the causal relations. One example is if we are interested in climate change, you'll know that permafrost is an important parameter, but they are beneath the, let's say, the Earth's surface. Therefore, it's not possible to just detect permafrost. Instead, you need to basically use the spatial temporal relations to figure out the disturbances caused by permafrost thawing. And we work a lot on generalizability and transferability in order to really enable large scale, even global scale, but also actionable information, meaning that you have a bit controlled quality across various geographic regions. We work heavily on uncertainty quantification, where Nico also tried to do this with the forest application, meaning that not only provide any kind of a visual appealing results from satellite data, but rather trying to also give a quality score. Therefore, it's important to quantify data model uncertainty, but also give a warning signal if there is out of distribution application of the model. Of course, the list goes on and on. Explainability, quantum machine learning ethics, but I guess this probably is not the really the focus here. And what we are talking about belong to the thematic focus we put on green AI. So meaning self-supervised learning, unsupervised learning, but also foundation models, how we can learn general representations from the super huge big data archive we have, such that we're able to support downstream applications in a more labor efficient or energy efficient manner. So this is probably only 2 slides I give in the beginning to give you a little bit overview of what we are doing in general. But for these 45 minutes, maybe I'm too ambitious, but I basically try to go through these 8 questions with you related to Earth and climate foundation models. Starting with what is the foundation model. So since you guys have already had SSL lecture yesterday, then there is geolocation embedding self-supervised learning in the morning. So I guess there's a consensus. What is the foundation model? Nevertheless, could anyone give me your understanding of the foundation model? Because this is usually the start of the discussion, and different people have different view on this. Is it interactive or is supposed to be that? Okay, yeah. Any different view on that? Yeah, I guess with. Yeah. Already one important feature of the ideal model. Any other opinions here? Yeah. Yeah. So you guys already go beyond what is foundation model, but we already discussed what is the idea as the climate foundation model. Well, here is just a link to the paper I'm more or less presenting today. If you want to read more detail, just scan this QR code, and later on you can have a more detailed look of individual list of answers to these questions we have. Yeah, so this is the definition from the Bamasani paper 21, which is very much cited. It's defined a foundation model is trained on broader data, generally use self-supervision, as you learned yesterday, and it can be adapted to a wide range of downstream tasks. So this would be without any, let's say, extra domain, let's say, speciality, how a foundation model is defined. Of course, I don't need to spend time on these examples of language foundation models. I guess you're all experienced from that to today's ChatGPT evolution. And also there is a big, let's say, evolution of the vision foundation models. Start from the transition models where you just use ImageNet data to pre-train some of these backbones. But now basically we have models that take text and video prompts. But also very recently with the ChatGPT 4o, there is a really heterogeneous modality, you name it, audio, video, image, text, and so on. More go to the domain of generalist foundation model. Yeah, but if we talk about foundation, Earth and climate foundation model, so this would be basically our view. On the left-hand side, we have different data sources. If you're from EO, definitely radar, optical data, point cloud data, but also with text data, meteorological data. And of course, since it's a foundation model, we are supposed to have it supporting various downstream tasks ranging from wildfire detection, tropical cyclone detection, or even, let's say, weather forecast. And in the core is the Earth and the Climate Foundation model. And here we need to think about different spatial, temporal scale, and the time span of Earth observation, weather forecasting, and the climate. So there's the interplay of these three kind of experts. And since we're talking about a physical world, we would really care about the physics consistency between this foundation model and the physical model we have, right? So this would be how Earth as a climate foundation model looks like. And of course, we want to benefit from the development of large language models. There is interaction with the human. And on the left, we want to interact with the physical model, like Earth system models. And in order to train any kind of foundation model, the first thing is which kind of data do we have? If we talk about Earth and the climate, I guess this is known to everyone, particularly what you see on the screen. We simply collected some completely open and free data source. What you see, Landsat, Moody's, and Sentinel is rather from the EO and the ERA and the SMIP. This is more from the Earth system science. And you will see that here today, we are having around 100 petabytes of data just from these 5 sources we have listed here. And also in this red dashed line, we have even labeled data, meaning that we could already learn, let's say, semantics or geophysical parameters from that. And you will see that today we are at the region of around 0.1 petabyte of data that are already with labels. And you may wonder which labels we are referring to. Here I'm giving you an overview, which is the data volume of labeled data starting from around 2008 till 2023. So you will see there is a big trend that the labeled data is also becoming bigger and bigger. And if you look at the tasks it addresses, then basically you see there is a big trend shift from the image classification type of problem more towards more challenging regression type of problem. If you are interested in all labeled data, here we actually did a service. Size of the circle is the size of the labeled data. Yeah, sorry, I forgot to mention that. So this is where you can observe the labeled data has become bigger and bigger. And then the color of the bubble stands for the task of the data, what is addressing. Yeah. So here, basically, you're interested in labeled data. To date, there are about more than 500 labeled data sets that are open for the community. We have made a service. It's also an effort led by Zhichong. We compiled a platform called EarthMats, where we have review and summarized all the data sets we could find in the community. And we also support more than 50 deep learning state-of-the-art models and provide libraries for more than 10 EO tasks. And we have used an NLP integrated approach that you could see the attributes of each data set, meaning that if you have any kind of application you need to work on, this would be a good, let's say, starting point for you to get a good understanding of what is already there, such that you don't have to label your data from scratch like we do maybe 10 years ago when we start with AI research. Well, yeah, so you see that this is basically the data we can base on. And why do we need Earth and the Climate Foundation model? On the one hand, it's about we can unlock the value of the big EO and climate data I showed there. What you see here is, as I mentioned, we have 0.1 petabyte of labeled data this is not yet just the open 1% of the full data archive, even though we're only listing limited resources. And on the left, you see typical EO data with the full spectrum optical domain. There's also microwave, of course. And on the right, you see the ERA5 reanalysis data, where we have about 60 land and atmosphere variables. You see the big diversity also of the data. So basically, there is a huge amount, 99.9% of the data that we could explore through self-supervised manner. And also, if we have foundation models, it helps us to enhance the label efficiency. So meaning that based on the general features you have already learned from unlabeled data, typically you are able to reduce the required number of labels to be about 10–20% of what you would actually need if you would train a model from scratch. And also reducing the carbon footprint. I guess the common practice in the community at the moment is still, if you have a problem, you try to train your own model. If we would have at least the general feature extraction part be done decently, at least we're able to basically reduce the carbon emissions caused by the training from scratch. And also, I see big potential if we have the Earth and Climate Foundation model, we will be finally able to bridge the EO and the climate science, which has a completely mismatch of the scale. So in EO, we are talking about 30 meter to 1,000 meter kind of resolution, if we only talk about spatial resolution. And if you go to the climate data, we are typically talking about 10 kilometer to 100 kilometer. And also, if you talk about the time span, EO, we are more talking about, let's say, time series of a few years. But for climate, if you don't have 3 decades of data, there's no climate. So if we now implicitly, through Earth and Climate Foundation model, put things together, then there is finally also the hope that we are able to bridge the scale mismatch between observation and the models. And finally, if we are able to bridge through the EO-informed improved Earth system modeling, then we are also probably able to improve ESM themselves, such that we are able to, for example, describe subgrid processes, which is extremely important. For example, if we talk about extreme events or any kind of local climate patterns. Okay, so this is why we need a Earth Climate Foundation model. Now we start about the idea Earth and Climate Foundation model. We have already heard quite some ideas before: multimodality, geolocation embedding. That's clear. But we also, for example, we need a balanced geographic representation. So if you claim something to be a foundation model, then it should work well everywhere on the Earth. At the moment, for example, many of these bench we're doing, for example, polar regions are completely missing. This is just one example. But also scale awareness. So if we are talking about EO data, if it's satellite data, probably we are talking about decimeter till 30 meter kind of range. Basically, the model should have the intrinsic scale awareness such that you don't have to give any metadata about the resolution of your data. It will be automatically possible to refer it to a kind of a characteristic length in the physical world, like a height of a floor, 3 meters, something like that. But it's completely automatic. And also, we have different wavelengths, starting from optical to microwave. The idea foundation model actually should have this wavelength embedding function that it can deal with any type of, let's say, wavelength range, but also number of bands, also different sensors. The time variable. So, well, if we talk about today's EO, this is something so trivial that we cannot treat every image of the same geolocation individually. Rather, basically, there is always a temporal relation in this data. And 6 multi-sensory, this is a bit related to 4. But I'm here rather talking about how to explore information from multisensory rather in a collaborative manner. That if you have been working with data fusion, you'll know that 1 + 1 is larger than 2 is not always the case. So it's a lot of, let's say, tricks there if you are still in the era of handcrafted feature-based kind of learning. And of course, the ideal model should be optimally, let's say, take advantage of multisensory data. 7 is trivial. So all foundation models should be task agnostic. It cannot be just supporting one particular task classification of this and that. Rather, it should really be working independently from the downstream tasks. And finally, it's also a very important point. I think the idea of foundation model is not that every group try to train their own Earth and climate foundation model by their own. In the end, we end up with thousands of Earth and climate foundation model. Instead, per design, this kind of foundation model should be rather carbon minimized in the training process. And also, we need to think about models that could be energy efficiently fine-tuned for various tasks. And of course, here, community effort is definitely necessary. Okay, so I will also talk about highly desirable feature later, but for each of these features, I would like to give some examples of the existing models. So if we talk about geolocation embedding, I here put an example which is tire to back. So they have triplet contrastive learning set up. So this means closed ties should be similar, and the distance the ties should be dissimilar. It's quite intuitive. And on the climate domain, they are trained mostly almost 90% on ERA5. They are per default actually, let's say, having the geolocation embedded. And I guess in the morning, you must have heard from Konstantin the set clip, and you have been probably already informed by his idea of image location contrastive learning. This is an example of geolocation embedding. Here is rather more explicit embedding of the locations. Regarding balanced geographic representation, one key is, of course, to have your let's say, data that you used for self-supervised training be globally very well represented. So here I just provided an example of the data sets you might have worked with. SSL4EO, S12 is for Sentinel-1 and Sentinel-2, L is for Landsat. So basically here we try to basically do a kind of balanced geographic sampling. But of course, this is not yet ideal. It's just still very much focused on the cities. There are much more that could be done here to further improve. And for climate models, then since the resolution is rather, as I said, 10 kilometer to 100 kilometer, then have the global coverage is less of a problem than if we are talking about a half-meter resolution, for example. The third feature, scale awareness. Here I give the example of scale MAE, where you can see that they are doing the supervision by having a multi-scale reconstruction. And also in the very beginning, you see that there is a ground sampling distance position embedding. So this is how they are trying to kind of get the scale awareness, but this is not yet that the model is able to recognize the intrinsic characteristic size. Instead, it's hard-coded, more or less kind of GSD embedding. Wavelength embedding, this is what you will hear in the next 45 minutes by Jitong. So here we have introduced the hypernetwork to do a wavelength-based dynamic weighting generator, such that no matter which kind of number of bands, which sensor, which wavelength regime your input data is, it is possible to output a unified token that you can use it to train one foundation model for all sensors. If we talk about the time variable, here I put a set MAE as the example where you see the have encoder, and it has already the year, months, and hours more or less hard coded in the training process. And if you talk about a climate model, here I provide an example of Aurora, and where they have, you see on the right top, they have the absolute time encoding of the weather patterns embedded in the system. And if we talk about multisensory, as I said, it's more really about information, let's say, fusion of different modality. Here is one of the paper from my student E, which get accepted yesterday at the ECCB. It's called the DECO. And the intuition behind it is if we work with optical and SAR data, instead try to pull everything together. We rather try to learn the feature embedding such that there is a common feature representation of SAR and optical, but there is also green this and the blue, this unique characteristic of individual modality such that it's a flexible kind of embedding to allow both modality to have common share of feature representation, but they can also keep the characteristic of their own. SkySense is a very powerful model because they have actually characterized a few of these mass features I have mentioned before. But in when we talk about multimodality, you will see this is a typical way that you have for multimodality specific encoders. Then you try to put them together, then you try to learn your representation together. And of course, alternative would be like DOFA I introduced before, that we try to do the hypernetwork to harmonize the tokens before the training process. In the end, the good thing is then you have one foundation model can work for all modality. We actually, in the beginning, we are not sure whether this is an idea that it can work because we literally have one model competing with individual models dedicated to individual sensors. But we're quite happy in the end. It turned out actually cross modalities, they can really support each other such that it can better serve the downstream tasks. Oh, task agnostic, I guess this is placeholder, you know this already. So we need a foundation model to support various tasks. And finally, for carbon minimization, here we give an example. DOFA, as I said, one model for all. You don't need to train one foundation model for one modality, but also it's reflected in the training process. Like DOFA, GFM, or SoftCom, they are all using efficient continual pre-training from the vision foundation models in order to reduce the, let's say, the training effort. Okay. Yeah, these are the must features of the idea as a foundation model. If you have additional, let's say, ideas, you are welcome to reach out because we're really interested in having a comprehensive concept of such an Earth and climate model. But there are also a few highly desirable features. For example, uncertainty quantification. So this is defined by the domain. In Earth observation, every output is considered to be a geodetic measurement. Therefore, for the foundation model, it should have also this property, meaning that if we have a pre-trained weight, it should not be a deterministic weight, rather we should learn the distribution of the weights. And also the physical consistency, this is a big debate. We all know that we are living in a physical world. There should be a certain consistency there, but it's, well, for some simple things like spatial temporal, let's say, continuous change, that's easy. But if you really go to physics like mass conservation, momentum conservation, well, you always need to decide for a good degree how much physics you put into the model such that it's beneficial. Because the main reason is that in your observational data, there's always errors in that. So you need to figure out a balance there. And finally, the AI assistance. So well, we turned it AI assistance. Basically, what we meant is, on the one hand, we want to profit from the development in the VLMs, such that there is interaction between human and these foundation models possible. On the other hand, we should really be able to train a system that are able to automatically define subtasks of a task to guide us how to do AI for various applications. Okay, this is the idea foundation model. Now I also want to touch upon a bit Earth and climate model. I guess most of us are from EO, but if we talk about weather and climate forecasting, basically, if we are talking about predicting in 0 to 2 hours, it's called nowcasting. But the current very hot papers like GraphCast, GainCast, and so on, the more addressing this medium range forecasting, which means 2 hours to 2 weeks forecasting. But there is also seasonal forecasting, and the true climate model then is really talk about up 3 decades or so. So these are basically the range of time we're talking about. I would like to give examples of 2 SOTA weather and climate foundation models. The first one is Pangu weather. So this is a paper published in Nature 23, and it uses multi-resolution and also long historical weather data to do the prediction in the future for 1 hour, 3 hours, 6 hours, and 24 hours. The advantage is really high resolution. It goes to 10 kilometer scale. And the architecture used here is VIT. And this is the first weather foundation model that's possibly outperform traditional numerical models like the ECMWF. Of course, there is also evaluation from ECMWF, but this is really the first time that you see there is such a potential. And of course, another one I want to give not a GainCast, because GainCast, there is also physics there. Rather, I stick to GraphCast from Google. And they have been using graph neural networks to represent the data as a graph. And they have been using the current and 6 hour earlier data to predict 6 hour ahead. Since they are using this kind of graph relations, the real advantage of this model is that it provides accurate prediction by capturing spatial dependency efficiently, meaning that it's really good at forecast extreme events and local climate patterns. Yeah, so I introduced probably 10 or more EO and climate foundation model. Here, basically, you see an overview. For EO and climate, we selected 6 representative models, including on the left, DOFA, SkySense, SAC-MAE, SSL4EO, scale MAE I mentioned today. On the right, you see GraphCast and Pangu weather. So you see that most of these models, not only 1 or 2, focus on only a few of must-have features. And you see on the right, basically whatever crossed as green, meaning this foundation model already have such a feature. But you see a lot of red cross, in particular in the EO domain, meaning that there's actually a lot to be done if we really want to have this idea Earth and climate foundation model. And another thing is you can see from the x-axis, which is the spatial resolution, there is a big gap exists in order to connect observational data and the climate foundation models. So reaching basically from 10 meter, 30 meter here up to 10 kilometer. Okay, so in order to achieve this idea, Earth and climate model, we have also provided some thoughts how to address various things. Due to the time constraint, how much time do I still have? Okay, yeah, then I don't go to detail. So for example, maybe only one thing. We talk about EO weather and climate, how to interact. In our opinion, probably with geographic mixture of experts might be a promising way to go instead of, let's say, push this model to work as one model. Yeah, but for more details, you're welcome to read the paper. And the last 2 points I want to talk is one of them is evaluating foundation models. So if there's one foundation model, one key measure is it should work for various downstream tasks. Therefore, there are quite some contribution from the community. This is from Alexandre et al. The proposed STEM bench, which have defined 15 tasks which are oriented towards 7 SDGs, basically to evaluate the foundation model with these 15 downstream tasks. Alex also led an effort we are contributing. It's called a GeoBench. So here we have defined 6 classification, 6 segmentation tasks. And the good thing here is we're really covering the whole, let's say, resolution range of EO, and also multimodality of the data, as well as different tasks. Of course, we did not introduce object detection regression problem yet. This is still to be done, probably in the GeoBench 2. And here is just an overview of these 12 tasks. When we talk about evaluating foundation model, we have a climate bench, and most of the foundation model is evaluated on A5 reanalysis data. So a very well-known example is from Stefan Rask et al., the weather bench and the weather bench 2. But there is still also a gap when we try to evaluate foundation models. So the requirement for a proper benchmark to evaluate foundation model, including it should consist of downstream tasks that address diverse data source, and it should have all the tasks represented, like classification, regression, segmentation, object detection, change detection, and etc. And also there should be interactions between components. If you look at today's benchmark, then there is still a big gap. For example, there is not a consensus on foundation model adaptation protocol. It's more linear probing, or it's fine-tuning, or it's parameter efficient fine-tuning. What is the protocol to evaluate? And there is certain regions which are not included, like polar regions. And also there is a lack of real-world scenario because most of these bench are basically based on the open lab benchmark data sets. And then there is no connection between EO and the climate, and there is a lack of standardized benchmarks of tasks. Okay, so what comes after? We already have an idea of foundation models. So a few keywords, parameter efficient fine-tuning, of course, but also model unlearning, continual learning, all these adversarial attack, because if foundation model becomes the backbone, then we should try to avoid there would be any kind of attack to the foundation model itself. If you're interested in all these details, in Munich, September, we are organizing a ML for Earth foundation model workshop, which is followed by a hackathon where we teach people how to do parameter efficient fine-tuning based on existing foundation models. And also, if you're interested in getting contact with the AI4EO, let's say, community, we're organizing a symposium in 2 weeks, which is free for registration. And yeah, we are discussing all these kind of topics also in Munich. Here is my concluding remarks. So I hope you agree with me that Earth and climate foundation models, they have enormous potential, but we are just scratching the surface. As you see, many of these features are not yet there. And finally, since foundation model is supposed to be something foundational, it's really a community effort. So there should be more coordination of this effort in the community such that we don't have yet another foundation model, but let's try to work together and work for one decent one, so to say. Yeah, that's all from my side. Thank you.